In the previous videos, we've been looking at the electric field due to point charges, and we found an expression like this. We said if you have a little point charge there, for example, oops, make that dot, there we go. If we have a little point charge there, charge Q, let's say, Q, and we want to know the electric field at a point over here. If this is a positive charge, let's say that's Q greater than 0, then we found that the electric field points away from the point charge, so it points this way. And we found an expression for it using Coulomb's law, thinking about the force between charges, but then dividing by the charge that we put out in this at this location. We found that the electric field can be written like this: E equals K. So K is that 1 over 4 pi epsilon naught. Q divided by distance squared. So there's a distance between the charge and the point. And then we have this little r hat unit vector thing there. And so what is that thing? That thing, again, remember, is this little tiny vector that points from the charge toward the point you're talking about. And so no matter where that point is, whether it's there or over here or down here, that r hat points toward it. So r hat is a vector that depends on what point you're talking about in space. So any other point in space, for example down here, we can then draw a different r hat. It goes this way. And if this charge is positive, as we say it is here, then the electric field is all this positive stuff times that r hat vector. And so the electric field is a positive number times this arrow. And we draw that electric field arrow then at the location where the electric field, where we're evaluating the electric field. So we don't, you can draw vectors kind of wherever you want really, but as long as the length is correct and the direction is correct, it's the same vector. But we draw it at the point. We draw it so that its tail is at the point that it represents, the point where we're measuring or calculating the electric field. So for a positive point charge, the electric field points radially away from it everywhere. If the point charge were negative, then this would be a bunch of negative. This would be a big negative number, some negative number, times r hat. The electric field vector would be opposite these r hat vectors, pointing toward the charge. So those are point charges, and we can do, and we did the dipole, and so we did combinations of point charges. And so for a point in space, if we had another Q, say over here, maybe this Q, we'll call it Q2, maybe that charge is negative, so maybe we have two charges, this charge here and this charge here, and we want to calculate the electric field at different places. We could call this charge Q1 now over here. This would be the electric field E1 that charge produces, so we'd clearly specify that. But now this charge also produces an electric field at this same location. And so if this is a negative charge, the little r hat vector still points this way toward the point that we're talking about from this charge. This would be the little r hat vector for this charge, for this point. And since this is a negative charge, the electric field that it produces at this point is going to point toward the charge. So we could draw an E2, maybe the E2, maybe it would be a bigger thing. I didn't draw that very well, but maybe the charge 2 is much bigger, and so it's going to produce a stronger electric field. So we have an electric field vector pointing away from charge 1 because charge 1 is positive. We have an electric field vector pointing toward charge 2 because charge 2 is negative and maybe it's bigger. And of course the distances matter. There's two different r values there, and then this distance here. So all those factors come into play, and we calculate each individual electric field, but then we add these two vectors together. We'd have to do a vector addition to find the total electric field. So we can do a bunch of point charges. It's easy to do point charges. It just might be a lot of work to break everything down into components and add everything together and find the total electric field. But what do we do if we have what we call a line of charge or a continuous distribution of charge? So something that looks kind of like this, and we'll draw it kind of vertically here. So we've got this line of charge like a rod, and we think back to the beginning of the chapter where we talked about charging rods, glass rods, plastic rods, rubbing them with silk or wool. We have this object, this physical, not point object, an extended object that has charge spread out on it. So there's charge everywhere spread out on it. We can think about this thing as having a total length L, so the total distance here is L. And it has a total charge Q, so the total charge, we'll call it capital Q. So there's charge spread out everywhere on this thing. It isn't just a point charge. There's charge spread out nice and uniformly, we'll assume. It doesn't have to be uniform. We can talk about examples where the charge distribution is not uniform. Maybe it's more densely charged on the top and less densely charged at the bottom, or something like that. So how do we calculate the electric field of something like this at some point in space around it? And you could pick any point you want, but there's some points that are going to be easier to calculate than others. So what we're going to do is we're going to think about a point that's directly out from the center of the rod. So let's draw an x-axis, an axis that bisects the rod. Call this the x-axis. And let's consider a point on the x-axis where we want to calculate the electric field. So we're choosing this point because of symmetry, and as we'll see, it's going to help us calculate the electric field. Any other point, a point up here, a point down here, we're not going to have that symmetry. We can still calculate the electric field, but it'll be a little bit trickier. It'll be a bit uglier in a sense. So we're going to use this point here. We're going to calculate the electric field there. And we're going to say that this is a distance d away. So little d is our distance that this point is from the center of the line of charge here. So the charge has a length L, the rod has a length L, and it has a total charge Q. So what we want to do is we know this equation up here. We know the equation for the electric field of a point charge. We'd like to use that to see if we can somehow use it for this thing, for this line of charge. How do we use this for this line of charge? Well, this is valid only if the charge is a point charge. Only if this charge here doesn't have to be a tiny amount of charge, but it has to be physically a small thing. And so how do we don't have a physically small thing here, we have a big thing. So what we do is we break it into pieces. We take this line of charge and we just break it into little tiny pieces. So let me just kind of shade one in here. And ignore the thickness of this line, the left and right thickness of this line. Just assume it has a length, and we're not going to worry about this thickness here. We're just drawing it to be a little more clear. So, but that's a small piece. That kind of vertical dimension right here is a small length, a very small length of this total length. We could call this like delta L or something, a small change in length. Or in calculus terms, we can call it dl. Or let's refer to the axis that we're on here, the coordinate axis. This is the x-axis that's perpendicular to the line. So let's run a y-axis parallel to the line, right down the center. We'll call this the y-axis. So this distance, this thickness here, the thickness of this little piece, we're going to call dy, an infinitesimally small piece of length. An infinitesimally small piece of our line. It's very tiny. And it doesn't have to be tiny, but in terms of calculus and the mathematics that we're going to do, making it really, really small is going to help us, as we'll see. Okay, so this is a very tiny length. This has units of meters, right? So what we need to do is we can use this. We can use the point charge equation then to find the electric field of this little tiny piece. Again, ignore this horizontal dimension of this. Just assume it's also very thin, but we're just drawing it a little bit thicker so we can see things more clearly. But this being infinitesimally thin here, this is a point charge. This is a very tiny, infinitesimally small, physically small thing, and there's some charge there. So we can calculate the electric field that this little thing gives us by using the point charge equation. And so what we'll do is we'll first draw a diagram, and then we'll write down an equation for just the magnitude of the electric field that it produces. So think about this as being a charge located on the y-axis, and just ignore the rest of the rod for a second, the rest of the line. We want to calculate the electric field that this produces at this location here. So we first think about, we'll assume this is all positive charge. All right, so we first think about the direction of the electric field from this positive charge at this point. Well, let's draw a reference line that goes from that charge to that point. So let it look something like this. And that's r. That's the distance r. That's in the denominator of the electric field equation for the point charge. So the electric field from this little tiny positive piece is going to point away from it at this location. So let's draw a little arrow like this. I'm going to draw it kind of long, but just so we can see it more clearly. So there's an electric field at this location because of this little tiny positive charge up here. We're ignoring the rest of this rod, just this little tiny piece. The little r hat vector would be pointing like this, down this way. And we'll just ignore it for now. But we know it's pointing this way. This is positive, and so the electric field's in the same direction as r hat, and we'll draw it over here so that the tail of the electric field arrow is at the point that we're interested in. So we have this distance r that we would plug in here. We have k, of course. K is just a number. What do we put in for q? Well, we put in whatever charge this thing has. So we have to think about how much charge does this little tiny piece actually have. How do we calculate that? Well, what we do is we think about the fact that across this entire length of the line, this whole length L, there is a total charge Q. So what we do is we define something called the charge density, or more specifically for this example, the linear charge density. We typically use the symbol lambda for that. You might find other symbols in other textbooks, but lambda is pretty common. This is not wavelength, as you might have seen in wave discussions. This is using lambda as a different thing, a different quantity. This is the charge, total charge divided by total length. And this is what we call the linear charge density for something that is uniformly charged. So we're assuming that the charge is spread out uniformly on this thing. And so this thing has units of coulombs per meter. Coulombs per meter. And so if we took a certain number of meters, like if we took half of the rod, and we took lambda and multiplied it by half of the length, whoops, that's not half the length. Let me change that. Multiplied by half the length, there we go, L over 2. What do we get? Well, if we take lambda is Q divided by L, multiplied by L over 2, the L's cancel, and we get Q over 2. Right, so that makes sense. If we just have half the rod, we're going to have half the charge. That makes sense. Well, what about if we have a really, really tiny piece of the rod? Really small, not half, not even a quarter, not even a third, not even an eighth or a tenth or a 100th, something really tiny. Well, all we do is we take lambda and we multiply by that little tiny length, and we get the amount of charge that is on that little tiny length. But notice that this little tiny length is infinitesimally small. All right, now there might be some confusion here. Be careful. This dy does not mean d times y, so that's not the same as this d. We're using this calculus idea of infinitesimally small things. And so this is lambda times a really tiny quantity, really tiny length. Well, we're going to get a really tiny charge. So we're going to call it dq. We'll call it d big Q. Infinitesimally small charge. So we're using big Q as the charge of the rod. This is an infinitesimal amount of it because we're looking at an infinitesimally small piece of it. And it's going to give rise to an electric field. Technically then, this electric field is also going to be infinitesimally small because we're using the point charge equation to calculate it, and the number we're putting in here in the numerator is infinitesimally small. And so we'll call this electric field dE. It's an infinitesimally small electric field vector. Really tiny thing. So I've highly exaggerated its length here, but I can't draw infinitesimally small vectors. It's kind of hard. I'll have to practice a little bit. So that's a little tiny electric field produced just by this point. We haven't even considered the rest of the rod here. But let's think about calculating the magnitude of this. Right, let's just think about the magnitude of this electric field piece, this little tiny contribution to the electric field at this location due to this tiny little piece of charge here. Well, we just use the point charge equation. Just find the magnitude of this. It's just these numbers here multiplied together. R hat just gives us direction, and we've already indicated the direction down here, and we can find an angle and maybe break it into components, and we'll do that in a second. So dE, the magnitude, just the magnitude of that vector, is just k times the charge, which is dq, divided by that distance r squared. And this distance r squared is this distance, this sort of hypotenuse distance here. So that's our magnitude. So we can think about an angle now. We can break this into components. There's an angle theta there. And if we were to take then, we can maybe write that angle in terms of some other things, as we'll see here in this triangle here. We can write this in terms of ratios of some sides. But before we do that, we can see that if we took this magnitude of this vector and multiplied by cosine of the angle, that would give us the component parallel to the x-axis. So let's just write that. So dE sub x, the x component of it, is simply going to be k, oops, what happened to my equal sign? It's very strange, it looks like a z. Very weird. All right, so there's the equal sign. So dE is equal to k dq over r squared times cosine of theta. Okay? And then you could say, what about the vertical component? What about a component perpendicular to the x-axis? Well, that'll be dE sine of theta. So we can write that down if we want. Let's just think about that for a second. Keep it in the back of our minds. But we can then think about what happens now when we look at other pieces of this line of charge. Think about other parts. For example, a piece down here somewhere. We can look at a piece down here somewhere, anywhere down here, but let's think about a piece that is sort of symmetric to this piece, totally opposite this piece. This piece is a certain distance from the origin. Now let's actually label that distance. Let's actually call that y, because we've placed the origin of our coordinate system at the center of our line of charge, and so that position of that point is the y coordinate for that point. That's how far it is from the origin. Well, let's think about a point that's the same distance below, so at a position of negative y. And we can just fill that in, make it look at least approximately close. So there's another piece down here that's exactly opposite this piece on the opposite side of the origin. Well, what kind of electric field will it produce? Well, if you think about, again, this distance here is r, and if this is the same length as this, and we have d is the same distance here, r is going to be the same for this charge down here. And this charge is infinitesimally small, just like this one. This one has a charge dq, this has a charge dq. R is the same as well, little r is the same as well. So the magnitude of the electric field that it produces is going to be identical. K dq over the same r squared. And then, because of the symmetry, the angle is going to be the same too. So we're going to have a little contribution to the electric field that looks just like this from this point down here. And those two components, those two pieces then, will have the same x components but opposite y components. You can see that if we just considered these 2 points, this little piece up here, a distance y above the origin, and this one down here, a distance of negative y, or a distance of y, but on the opposite side of the origin, they cancel out in their non-x components. Their y components in this case cancel out. And so all we care about ultimately are the x components of everything. In other words, because we've chosen a point that's directly out from the origin, out from the center of the rod, because of the symmetry, any electric field contribution from points up here will have vertical components canceled out by points down here because of that symmetry. And those opposite points will have equal x components. So thinking about symmetry allows us to say we don't even need to worry about calculating dEy. We don't even have to worry about coming up with an equation for the y components of this electric field vector, because we know that once we consider all the different points on this line, there will be opposite points whose y components cancel out. And so we know that will happen. We could show this mathematically. You could still do all this and show this mathematically, that you get 0 once you add them all together. And you can do that as a little homework assignment if you'd like. So we're just going to say by symmetry, the y components all cancel out. So it's only the x components that we have to worry about. So we're going to take this expression now, dE sub x, and we need to add up all of these different terms for every different point. As we look at all the different points from the bottom of the rod to the top of the rod, they all have different contributions to the electric field at this point here. They all have different angles. They'll all make different angles, but again, opposite points will make the same angle. All right. There'll be different r values as we go from points down here to points in the middle. The r value, the r distance changes, so there's different things that change. So just like with the point charge situation, if we have 2 point charges, we have to add 2 electric field vectors together. If we had 3 point charges, we'd have to add 3 electric field vectors together. Well, how many point charges do we have here? Well, we're breaking the rod up into infinitesimally small pieces. And so to make a finite-sized object out of infinitesimally small pieces, we need an infinite number of them. And so how do we add together an infinite number of infinitesimally small things? infinitesimally small electric fields. How do we add those together? We do an integral. We have to do integration. And so what we do then is we say we're going to integrate. We're going to add together all those little x components, dE sub x's. We're going to add all those things together. That's going to give us the total electric field, the total x component of the electric field. And we had said because of symmetry, there is no y component. Once we do all this addition, all the y components cancel out. So this really is going to be the total electric field, period. Not just the x component, it's the total. There is only an x component for points on this axis that comes straight out from the center of the rod. So we do the integral by plugging in what we found that dE sub x was. So we put our little integral symbol there. And we put in here k dq over r squared cosine of theta. Okay. And so we can substitute some things in here to make this into an integral that we can do. So what we want to do is we want to write all this stuff in here in terms of a single variable that's changing as we integrate, as we add together all the contributions from all these little points that make up our line of charge. And so what's a variable that kind of identifies the different points that we're at on this line of charge? We can use the y coordinate of those points. If we think about the y coordinate as being something that uniquely identifies every point on the line, going from down here to up here. In fact, if we're cutting the line in half, we're going to be going from negative L over 2 at the bottom to positive L over 2 at the top. Those will be the limits of our integration if we use y as our variable of integration. So then the trick is we have to express everything inside this integral in terms of y. So how do we do that? Well, we can use the Pythagorean theorem for r. R is a hypotenuse. D is one side, y here is the other side. For any given point on our charge, on our rod, y is this side of the side of the triangle, d is this side, and r is the hypotenuse. So we can write that out, and we'll write it here. So r is equal to the square root of y squared plus d squared. Or we can say y squared plus d squared to the 1/2 power. Right. What about this cosine of theta? Well, here's the angle theta, and if you think about this triangle here being similar to this triangle here, this angle there is the same as this angle here. If you think about two lines that cross different geometry identities and so on, these two angles are the same. This one, and we'll draw this one up here. These are two opposite, call them vertex angles or something. There's different terms for these, but this is theta. And if we then look at this triangle, this is a hypotenuse, y is the opposite side of this triangle, d is the adjacent side, and so cosine is what? Cosine is adjacent over hypotenuse, right? The adjacent side d divided by the hypotenuse r. So this integral is now going to become the integral of k dq, and then we have an over r squared, but this cosine is going to be d, the adjacent side, divided by another r. So we really have an r cubed. So we'll put the d out here for now and put an r cubed there. So d divided by r is your cosine, and then the r squared is already an r squared down there, so we have ultimately an r cubed. So we're getting there. We again can plug. D is just a number. D doesn't change. It's a constant. Right? We're always at this point. We're considering this point here a distance, some distance away. It's y that is changing, and therefore r is changing. But we still need to get y in here more explicitly. We can have it in here inside of the r variable, but you need like a dy somewhere in here. Well, that's where this substitution comes in. The linear charge density times that little tiny thickness, that little tiny length dy is your charge dq. So now we put that in the numerator. So the integral we have to ultimately do looks something like this, and we're just going to call this e without an x subscript on it. We have the integral of k lambda dy over r cubed times little d. That little d is again just a constant. And then we can rearrange a little bit. Let's plug in the square root of y squared plus d squared for r. And so we'll have the integral we'll write all this stuff up on the numerator. So k times d times lambda times dy, write that a little further away, and then divided by y squared plus d squared to the 3/2 power, because it's r is cubed. R is the square root of y squared plus d squared, but then we're cubing r, so the denominator is going to be to the 3/2 power. So that's the integral we need to do, and the limits again are whatever the values of y starts at and goes to. So minus L over 2 to L over 2. So this is the idea behind doing continuous charge distributions. You break them into small pieces such that the small pieces can be treated as point charges, and you use the point charge equation to calculate the electric field that that little tiny contribution gives you at this point, at some point. And then you integrate, you add together all the contributions to the electric field at that same point. And if there's sufficient symmetry, you might be able to take some shortcuts and simplify some things. So now we've got this integral to do, and we have some constants in here. K and d and lambda are just numbers, they don't change. And so we just have the integral dy divided by y squared plus something squared to the 3/2. And you can look these things up. You can look up integrals. We won't go through how to solve integrals in this case, but you can look these up. And what you'll get is something like this. You'll get the integral, or you'll get that the integral is lambda, and I'm going to write k. I'm going to start to write k. When we start to ignore k now, we're going to start to write k as 1 over 4 pi epsilon naught. So I'm going to put that under here. Lambda divided by 4 pi epsilon naught. So that's our k. 1 over 4 pi epsilon naught is k. And when you do the integral, you'll get a d squared in the denominator, and so that's going to cancel this d in the numerator. So we're just going to have a single d in the denominator. You'll see this if you go through and look up what this integral is. But you get a y on top, and you get a d on the bottom, along with the y squared plus d squared to the 1/2 power. And that's what you get for the integral. You've got lambda and k, and then a d again. There was a d squared here when you do the integral, but there was already a d on top. That's why we just have the single d on the bottom. And then we evaluate this between the limits. Negative L over 2 to L over 2. And so when you put your limits in now, you'll put the upper limit minus the lower limit. And so let's factor out. We'll factor out the lambda over 4 pi epsilon naught. So we'll just leave that out. Lambda over 4 pi epsilon naught. And then we'll put in the upper limit, which is L over 2 for y. Wherever we see a y, we put L over 2. So we have L over 2. And we have a d down here. And we have L over 2 squared plus d squared to the 1/2 power. And then you do minus the lower limit. And the lower limit is negative L over 2, so we put that there. So we put a negative L over 2 in the numerator, and then we have a little d in the bottom, and we have negative L over 2 squared plus d squared, and that's to the 1/2 power. And so that's what we get. And now you can add things together. Notice these don't cancel. We've got negative and negative, so we actually have two of the same terms, positive. And so we have two of these same things, and that cancels out this 2. And so what we get is we get lambda over 4 pi epsilon naught, and we have L on the top. There's an L over 2, we get a plus another, minus minus, plus another L over 2, so we just get an L on the top. And then we have a d, little d. And then we have L over 2 squared. We've got the minus L over 2 squared here, plus L over 2 squared there. Those are the same. So we get the L over 2 squared plus d squared to the 1/2 power. And you could leave it like this. This is E. This would be the magnitude of E. And you could calculate, we'll write it in one more step, but you could calculate the electric field at a point D from the center of the rod with this expression. So The length of the rod is in here, the linear charge density of the rod is here, some constants are here. The only variable that is in here is the distance d that we are from the rod. And so this would give you the magnitude of the electric field at points away from, straight out from the center of the rod. And we would know, this just gives you magnitude, but we would know that those electric field arrows would point straight away, perpendicular to the rod along this x-axis. If we looked at different points above and below the x-axis, then we wouldn't have the symmetry to be able to say that the electric field points straight to the right. It would point at an angle, and in fact we'll look at a little simulation of what you'll get. So let's just do one more modification of this. Remember, this lambda here is the charge, the total charge divided by the length. So we've got total charge divided by length, but then times length. So the product of lambda times L is just the total charge. And since we're talking about magnitude of the electric field, let's put absolute value of the charge on here. So we can write this as 1 over 4 pi epsilon naught, the absolute value of the charge Q, divided by the distance d times L over 2 squared plus d squared to the 1/2 power. So that's maybe a more final expression. If the charge is negative on this rod, then what is the difference? Well, if the charge is negative, then all these little charges here are negative. All these electric field vectors point in the opposite direction. The vertical components still cancel out, but the total points toward the line, toward the rod. And so the only difference is the direction of the electric field, toward it versus away from it. The magnitude is still the same. So here is our equation for the electric field of a line of charge, but only on this, what you might call its perpendicular axis, if you will, for points directly out from the center of the rod. Okay. So we'll look at a little, see what this looks like in a little animation in a second. One question we might have, though, is what happens if the rod gets really long? So if we consider just two things, let's consider another point just above this. Just think about a couple of changes that might occur. So a little point just above that. If we think about the electric field at these different points, the electric field from this point here is going to point something like this. I'm going to draw these a little bit smaller. So there's going to be electric field at this other location from all these different points of this rod. So for this point that's not on this x-axis, that's not straight out from the center of the rod, it's out from a point here where there's like more charge down below it, less charge above it. And so there's going to be electric field pointing kind of down and to the right from points up here, but there's going to be a lot more points that have electric field pointing kind of up and to the right. And so so for this point here, your electric field might point something like this. And there's going to be other points that point like that, or like this. You're not going to get the same vertical component cancellations as you take into account all these different pieces for points that are not on this axis, on this x-axis. In fact, what you'll get, as we'll see in a second, to erase these arrows, what you'll get is an electric field that points a little bit upward like this. Total electric field that points a little bit upward, because there's simply more positive charge down in this direction, kind of below the y-coordinate of this point, than there is above the y-coordinate of that point. You'll get an electric field that points this way. And so we'll see what that looks like. But let's think about what happens if you were to take this line of charge and make it really, really long, make its length really big, and we can even think about its length going to infinity. So we'll do that eventually. But if this length gets really, really long, the longer this length gets, the less important that difference is about there being more charge below this position's y-coordinate and less charge above the position's y-coordinate. The longer this rod gets, the less difference that makes. And so what you'll find, and what you might think you're going to find, is that, yeah, if the rod is kind of small, and this point is a decent distance away from the point that is on this axis, then there'll be a significant difference in the direction of these vectors. This electric field vector points along the x-axis, this one has a slight angle to it. But as the rod gets longer, that difference is less and less significant. And so you'll find that the electric field of this point starts to become more parallel to the electric field of these other points. the fact that this point is off-center doesn't make as big of a difference anymore if the line of charge gets really long. So we'll see that in the little simulation. But what do we do? How do we get an equation for the electric field if the line of charge is really long? Well, let's look at this equation here. If L is really big, the way we're going to write this is we're going to say if L is much larger than D. And there's different ways to think about this limit. This is like a limit as L gets really big compared to D. You can also think about it as a limit as D gets really small compared to L. In other words, keep the line of charge the same length, but make your point really close. Think about points that are really close to the line of charge. A point here versus a point here. Because that line of charge we're so close to it, there's not as big of a difference in what you'll see with the electric field between a point here and a point here than compared to what you see for a point here and here. The farther away you are, if the line of charge is more finite, the bigger that difference is. So we can kind of see that in the simulation, but there's two different ways to think about these limits. So what if the line of charge is really big compared to the distance D? So if you look here, you want to make some comparisons. Where are some places in this equation where we can actually kind of think about comparing directly L and D? Well, here they're being added together in the denominator. Right? I've got L over 2, but still, if L goes to infinity, so does L over 2. Half of infinity is still infinity. So if this is getting really, really big compared to D, we're adding a number. We're adding like 1,000 plus a centimeter. 1,000 plus plus 1, let's say, or something. All right, this becomes less and less significant. This D plus D squared here becomes less and less important, and so we can just ignore it. We can show this a little more formally, in sort of the calculus way, but you can kind of see that as L gets really, really big, this term becomes negligible, and so we're going to approximate this, and this becomes exactly correct, exactly equal if L does go to infinity. But we'll at least approximate it. If L is really large compared to D, then we can say that the electric field is approximately equal to, we've got 1 over 4 pi epsilon naught. We've got our absolute value of Q up there. We've got a D in the denominator already. And then what happens here? We're going to ignore the D squared term, and we're just going to kind of drop it, just erase it. And we'll just have L over 2 squared. But then we're going to take the square root of that. So it's just L over 2. So that looks much more compact. But then you might say, well, L is going to infinity. Isn't this going to be 0? Well, remember that if L is going to infinity, so is the charge, because we have a certain charge density. And we haven't said that the charge density is getting thinner, so it's not like we're taking the line of charge and it's not like we have a rubber band and we have some charge spread out on the rubber band and then we simply stretch the rubber band. What we're saying is we've got a certain charge with a certain charge density and we're increasing its length, keeping the same charge density. So if we keep the same charge density, as the length gets bigger, the charge gets bigger. So this ratio, this L is getting bigger and bigger, it's in the denominator, but this Q is also getting bigger and bigger, it's in the numerator. But we can see that what we have here is Q divided by L. And then we can bring the 2 up on top. So this becomes 1 over 4 pi epsilon naught, and actually we'll write it as 2 lambda. And we'll write it as absolute value of lambda because we had absolute value of charge. So the 2 is up there because the 2 was down here. Q divided by L is your lambda. And then we just have 4 pi epsilon naught times D. So that is a nice compact equation for the electric field due to technically an infinitely long line of charge. But to a very good approximation, it's the electric field due to a really long line of charge compared to your distance. So if it's a 1 meter long line of charge and you're 1 centimeter away from it, for a very good region of space in here, this equation applies. These points all in here have pretty much the same electric field pointing perpendicular to the line of charge, and they have this value as their electric field value. Or if the length is truly infinite, then it doesn't matter what your D is. It doesn't matter what your D is. If the length is infinite, any finite number is, infinitely smaller than infinity. And so this is your equation for an infinitely long line of charge. So let's look at this. Let's see what this looks like in a little simulation here. So here we have these little green arrows. We have this line of charge running along the x-axis. This is more of a horizontal oriented line of charge. And if you look at these points straight along this line that's perpendicular to the line of charge, they're pointing straight in that direction. And this is more of a three-dimensional picture. So if I rotate this a little bit, you can see those points are pointing away from kind of the axis of the line of charge. All right. And so, but what you notice, if we go back to this view, as you move further to the right of this line of charge, especially these arrows that are farther away, they're smaller. Farther away arrows are smaller. Notice the angle that they start to take on. They start pointing in a direction that isn't perpendicular to the line of charge. So this arrow here points more this way. And you can see that as you rotate along. You can see that with these longer arrows that are closer as well. They're pointing more at an angle. They're not perpendicular to the line of charge, to the axis of the line of charge. Except the only ones that are these here. All right, but now, and then if you look out here, the ones that are further away point at even greater angles. So these are pointing like straight away from the line of charge, because these points are almost on the axis of the line here. So you can kind of rotate this around and see what those different electric field arrows look like. So these are kind of complicated to calculate, but we can do it computationally very easily by just adding vectors, coming up with a process of breaking this down into small pieces and doing some sort of a loop where we add together the electric field contribution at each of these points due to all these small pieces. And so a computer can do this very easily for us. So if we think about, whoops, there we go, having some zooming problems here. If we think about what would happen if we made this line, this rod longer and longer, let's watch what happens here. Whoops, come on, it's misbehaving. There we go. All right, so watch what happens to these angles of these different vectors up here. For example, this one right here. Well, as we make the length of this line longer, watch what happens to the angles of these vectors right in here that are definitely pointing a bit to the right now. So here we're going to make the length longer. Notice how those arrows are becoming more and more perpendicular to the x-axis, more and more perpendicular to the line of charge. And if we make the line really long, and by really long, 10 meters is not infinity, but it's pretty long, all these arrows look the same. All these arrows are pretty much exactly the same. And then we can zoom around, we can look around, and everything looks the same, except for maybe the ones over here at the very end, perhaps, that are a little bit closer to the line of charge. And this is a 3D view too, so it's a little bit hard to tell, but if we kind of pan around a little bit, you can see how all those arrows are all pointing perpendicular to the axis of the rod, of the line of charge. So when we have an infinitely long line of charge, then all these electric field arrows are perpendicular to the axis of the line, and they decrease in strength like 1 over distance. So this arrow here is a certain distance from the center. This arrow here is twice the distance from the center, and so its electric field vector, this one right here, this electric field vector is half the length of this one, because it's twice the distance, the radial distance away from the center of the rod. So that is the electric field due to a rod. And again, we calculated it by thinking about breaking it into a bunch of small pieces, breaking the rod into a bunch of small pieces and treating each piece as a point charge, and then doing some integration. So in other videos, we'll look at other things like a ring of charge, and then we'll look at a disk of charge. The ring of charge is pretty easy. The disk of charge there's different ways of approaching it. But we can think of the disk of charge as being made up of a bunch of concentric rings of charge. We can add things together that way. And then we'll think about a sheet of charge. So those are some typical examples that we'll do. So until next time, have a good day.